Hey, welcome to the last unit in this first section on statistics. And if you look at the title at the top here, you can see we've got bivariate data. There's that word again, bi meaning two variables. And what we're doing is looking at the correlation, how they're related in company with each other. Correlation or correlation, it's said. And look, I reckon this one would be of interest to you budding young IB students. It looks at the variable of hours studied and the grade obtained in test scores. So it suggests that as you increase the hours studied coming along here, you get an increase in the grade. Can you see that as we go up there? And what we're going to do here in two podcasts now, one on basically looking at the correlation and then looking at whether we can predict if two variables show some associated behaviour, then in some sort of pattern, and here it's called linear, we're looking for that linear pattern as one increases, the other increases, or as one decreases, the other decreases, with a view to saying, is it possible to predict anything from this? Okay, what about coming down here? As the heights of people increase, generally the weights increase. And there seems to be some association between these variables. There's two variables. The variable here is the height and the variable here is the weight, and there is some correlationship or association or correlation, we say, between these two. This is an interesting area, isn't it? And over on the last one here, if people have a higher lean mass, a bit of biochemical work going on here, or health work, the metabolic rate tends to be higher. If you have more lean, mind you, lean mass in perhaps kilograms, then the metabolic rate is higher. So, can we predict when we study two variables and see if they're associated at all, can we predict where there's going to be a response in one as we change the other, and what sort of response might that be? Intriguing stuff, and starting to get very, very useful now. So let's come down and have a look at some definitions for a start, because the first thing we want to do is to plot the values, the pairwise values of the two variables, the bivariate data. We'll have a set of x values and a set of y values usually to go with them. Now there is a convention here, and this is very, very important. We always plot on the horizontal axis what we call the independent variable, Okay, so this is sometimes in rather junior maths called the explanatory variable, explaining what patterns are going on there. And then up here we have the dependent variable, or the one that seems to be responding to the other response variable. Now this is very important that you observe this, because in mathematics we look along this way along the horizontal axis and say, as this changes, what does the dependent variable do? So there is a definite choice here of this one being dependent upon changes in this one. So you must choose carefully when you're plotting bivariate data. And of course, the plot that we usually refer to here is a scatter plot. And we're going to go through right from the basics of how to draw that. So let's come down and have a look. I want to test you now. Here are pairs of variables, bivariate data, where we might have times and distance travelled, wages and time worked, fitness level and exercise time. Now, I want you to pause the presentation a minute and work out for each of these two variables in each case which one goes on which axis. Remember, on the horizontal axis down here, in each case, is the independent variable, the independent. So your choice here is to say which is independent and which is dependent. Okay, pause the presentation and work out what you would do here. Okay, I'm going to come back now and do it for you here. Now, as time passes, you expect the distance travelled to be dependent upon that time. So the independent type variable is time here, and put the units. When you're drawing a scatter plot, it's very important to do that, and also to have a mark scale. You've got a grid, but you've got to mark in 1 hour, 2 hours. This is marked very harshly. It's got to be a well-labelled diagram. And then the dependent variable, dependent on the time that passes, is the distance, and that's going to be up here in kilometres. 5, 10, hang on, we've got to get this right here. 5, 10, etc. So you must have a scale and units, but the position of these variables relative to each other is important. Let's look at the next one. Wages and time worked. As more time goes by, you earn more wages. So time is here, and this is in hours. That's the independent variable, and the wages depend upon that, and that's going to be in dollars. And again, you need to mark in some scale. No, just not just putting their units. It could be 5, 10, etc. You must put a number there as well in each case, whatever. It could be $50, $100, whatever. Okay, are you getting the idea of things? There is a definite process here. All right, what about fitness level and exercise time? All right, well, as exercise time changes in terms of the time spent on exercise, you expect your fitness level to improve. It should be in response to that. So down here, the independent variable in this case, let's remove all this now, would be the exercise time, whatever units you're putting it in, hours, and then looking how fitness level depends upon that, fitness level. Up there, and again marking in a scale, 2, 4, whatever you choose, fitness level. Don't know what these units will be in, 10, 20. So there is a protocol here, there is a process, a convention, and we always have the independent variable horizontally and the dependent variable vertically. Okay, just watch that now. Okay, let's go and look at how to handle some bivariate data, that is one variable measured and the other measured in partnership with it, and see what we can do with some graphing. Okay, let's have a look now. Here we are, they've already done the scatter graph. This is the lean mass one that I used before. Lean mass of adults on a dieting program. So as the lean mass increased, and we haven't got units. That's naughty there. So that should be kilograms, and calories burnt, the metabolic rate, calories per day or per 24 hours. That's, should put those in there. That's important. We've plotted the data, so let's just read a couple of data points off. At 40 grams, the metabolic rate was, whatever that is there, not on a graph paper so you can't read it properly, about 1180 calories per day or something. Okay, so does the scatter plot show that there is an association between the metabolic rate and lean mass? Yes, it does. There's a positive association. Now, what does positive mean? As one increases, the other increases. So that'd be a positive. They're both moving in the same direction. If one increases, and you usually talk about this one, the independent variable, talk about changing along here. As you change that, as you increase that, if the other decreases, that's in opposite direction, opposite movement, opposite direction maths, negative. Okay, so what would a picture of that look like? Okay, so you might say your percentage fat content and exercise time. As you exercise more, generally your body fat will come down. So as this increases, this is decreasing. Well, that's a negative association, or a negative correlation, as we'll say later on. It's how they're associated or moving together or related together or correlated. Okay, got the idea? Well, this is a good, interesting study. So let's go on and have a look what to look for in a scatter plot. And then we'll have a look at how to draw one using the calculator. As a rule of thumb, what do we look for? The overall pattern. That's form. Here it will be, in this course, always a linear form, but it could follow some sort of a curve, an exponential curve or something like that. But here we will be looking at linear correlation or linear association. So basically this looks like a straight line with a fair bit of movement around it in this case, but moving up there in a linear fashion. We don't have a curve for the data. It's not like that. So in this course we're only looking at linear correlation. And the direction, what's that? Well, we say as the independent variable increases, what is happening to the dependent variable? It is also increasing. So that's going to be a positive pattern or correlation. And the strength we're going to come to later. How strong is the pattern? As we move along here, how well do these follow the pattern of change? How close to the line are the points? How close to a linear or linear pattern? How close are they? Well, they look pretty close, but a bit of spread around there. We'll need to measure that later on. And then, of course, as with all statistical work, we should look at any outliers. Any points that are away from the main body of data, back in the other unit, or here, not following the same pattern, if you like, way off track, something like that. And we're going to have a look at that. So there, we should, again, perhaps discard them, but certainly discuss them and discuss why they seem to be following a different pattern or lying away from the body of data. Okay, let's keep going. You're building up an idea here of what we're looking for, and so let's have a look at some data here, and I've drawn this on the calculator in a minute. Now, so that you can have a bit of fun with this, I'm going to show you this data. There's a fair bit of it, so if you like to put this on your calculator, list 1, list 2 later on, I'm just going to pause it there. You can come back and do that if you want, and I'll just show you the rest of it. There's quite a bit of data here. There's the rest of it. Okay, so these screen clippings here are from Pearson's now, and so Pearson's textbook for this new IB course, and here are the two graphs. Why are there two graphs? Well, first of all, can you see that the data was city consumption in kilometres per, there we go, just come up here, in kilometres per litre, and highway consumption in kilometres per litre. And this set up here is containing an outlier, one that's way out there, and it's hard to actually summarise this data set with a point which doesn't seem to be following the same pattern. It's away from the main body of data, and we should look at that and then perhaps exclude it and look at in more detail this bunch here, and that's what's been done. This is no outlier included. And the reason they excluded the outlier here was not so much an error in measurement so much as this was the hybrid car. Had the capability of changing between electrical and fuel and electrical and fuel and petrol type means of propulsion here. So that was performing differently. Well, I don't know about so much differently, it was way outside, but it's still on that same linear track, but much higher values here and here. So let's exclude it there and look at the other more conventional vehicles. And can we see anything here? Well, I think we can. As your highway consumption goes up, then for these different types of cars, 34 of them, so your city consumption also goes up. So if you've got a car performing, what is this here? This is 14 kilometres to the litre, so that's really economy there. It will perform also highly on city motoring. So a car, there are 34 cars here, a car performing with high kilometres per litre on the highway will also have high kilometres per litre in the city driving. So there seems to be an association, and it's positive. As one increases, the other is increasing. So it's a positive association or correlation. It's linear, and we should say in the direction of it, as one increases, the other increases. And it's got quite a strong linear pattern, hasn't it? And you can draw a line through there quite well with a bit of deviation above and below. It's a fairly tight pattern. And we might want to develop some statistical tool for measuring how strong that linear pattern is, or linear association. Okay, let's come down, and I want to show you how to do it on the calculator now. Okay, so I've done here, the great calculator here, Casio 9860 Plus graphics display calculator. So let's come across here to this first window. So you highlight stat, hit execute, and you get this window, and you can see I've been busy. I've entered in some of that data. I haven't put it all in, I've only put 22 scores in. Okay, and then what have I done then? I have hit or chosen graph by hitting F1. Okay, and up comes this window, and of course, as before with graphs, we want to set the graph up, so come in here and choose F6. If you choose F6, then we've got these graphs, and if you choose graph 1 by F1, here it is up here, graph 1. If you now scroll down, so that will be using this button here, we highlight what it is, but it's set up as a med box from a previous presentation. Now, we don't want a med box there, so we have a look at the options, and here it is here right on the first window. We want a scatter graph. So come in here and choose that by using F1. And then we've got this window over here now, and it goes to scatter. We've got to scroll down again to tell it what's the dependent and independent variable. So come down, I'll just come down here a little bit, where we need to scroll down to that first X list at list 2 with that button, and when it's highlighted here, you'll see we want to change the list. I put highway motoring in list 1, and that's our independent variable. So to choose that list, I got to choose in there F1 and then push 1. Okay, list will come up list and push 1. So that's going to change here to, here it is, list 1 there. So you choose list by hitting F1, then put the number 1 in when prompted, and we have this window. Now I think that's okay, because I put the independent variable in list 1, that's X list, and the dependent variable in the Y list. You don't have a choice here. X list is on the horizontal axis. It must equal the independent variable. That's why I asked you back early in the presentation to choose which way around to plot those options I gave you. The Y list is the vertical list, and that's the dependent variable. You must have that right. Okay, so then if you hit execute, you come back to this window, and we'll just go down and finish this off, and we'll just I'll go up here a little bit. So here we've got to select which graph we want to draw, so that means go to F4 in there, and we get this window, and you can see, stat graph 1 is off at the moment, we don't want that. Stat graph 2 is on, so we need to scroll, well, first of all put that one on by choosing on, which is F1, then scroll down and get stat graph 2 off. So this is the pattern we want. We only want one graph, and that's stat graph 1 is the way I've got it set up here. Then if you hit execute, or just choose draw by using F6, then up comes your scatter graph. Of course, this is a scatter graph by technology. Don't go just blindly plotting that onto a set of axes. You really have to plot your own here from the original data. If it's asked in any exams or tests. Okay, but this one on the calculator gives you an idea, and if you don't have to produce a hard copy, this is sufficient for you to talk about what? Form, yes, it's linear, and direction, yes. As one increases, the other increases, so it's positive. These are the answers to these correct questions. And then strength. How close to the linear form is it? Pretty tight, but we still want to develop some number or statistic we can calculate to actually indicate that strength. Okay, let's go down and have a look at this idea. Correlation. This is what we're trying to do. How much association there is in company with each other, related together or in company. Well, let's have a look over here. How well does this fit a linear correlation? Oh, pretty good. It's a straight line, mate. It's perfect. What about this one? Oh, we've got some wavering away from a straight line. If you try to put a line of best fit in there. So that's not as strong. Still positive though, in all these cases here, as the independent variable increases, the dependent variable increases. So they're all positive. Just pause here. Association in bivariate data or between two variables is positive if an increase in one results in an increase in the other. They're both in the same direction. Okay, let's go across to this one here. We've still got, what? A basic linear form, I suppose, but, and it's still positive, but, it's not very strong association here. If you take a value here for x, it could be that low or up here. Not like back over here. Let's go back over here. Any x, you can say pretty tightly what y was. They follow a very tight pattern there, a tight association. There's a perfect association there, in fact. Well, this is even worse. There is seemingly still that trend, isn't there? As x increases, y is increasing, but it's a pretty weak association down there on the end. Okay, let's look at another situation. What about this? Well, it's going the wrong way, mate. As the variable, the independent variable is increasing, the dependent variable is decreasing. All the points are coming down, if you like. Again, though, this is in a very tight or predictable fashion, tightly following a linear model, following a line, if you like. That's a perfect straight line. This one, wayward again. That's negative as the independent variable is increasing, the dependent variable is coming down, and so on. We've done exactly the same pattern in negative land. And the strength of the association diminishes as we go across these four diagrams. we're getting less tightly associated variables. Okay, if it's a negative correlation, is if you increase in one, you decrease in the other. So negative, as usual, means the opposite direction in maths. So what we've got here is you usually say, let's look at an increase in the independent variable and look at how the dependent variable responds. If one is increasing, the other decreasing, opposite direction, it's a negative relationship or association, negative correlation. Okay, are you getting it? You can see, I think we need to get a measure of this correlation. Oh, here it is. Again, screen clippings here from Pearson's. Actually, those graphs just above there were taken from publication by Hayes and Harris. Okay, correlation coefficient measures the strength and direction, so it's going to be a positive or a negative number, and it's given by this form. Now, we'll look at what it is. This is for the sample. X bar and Y bar are the means of the two variables, and we're dividing by the standard deviation of those scores. And remember, they're paired here. The scores are paired, and we're then finding the mean of that as the sum of those products. It's often called the product moment, Pearson's product moment correlation coefficient, and we'll talk about that over here. And this is a sample mean of those products. Intake 1 because it's only a sample. Now, we don't have to make those distinctions here. I'm putting this in to pay courtesy to you as a budding young mathematician. Understanding the derivation of this is outside the course. So we're going to get the calculator to produce this value, and what our job is to understand how to interpret a correlation coefficient. It's given the symbol R. Now, and over here, this is the full name, the product moment correlation coefficient. Now, R over there from the sample, that's a sample value, and so it's R. The actual population coefficient with the Greek letter there, rho, is this one on n, and we're measuring the deviations of every member in the population away from the population mean, in each case of the two variables, the x variable and the y variable, and dividing by the population standard deviation of the two variables. Now, you don't have to do the calculation in exams, and we're not going to go into what Pearson's have there. You might like to look at it, an extensive treatment of how to do it by hand. We will be using graphics display calculator, and the symbol used on all GDCs is R. Okay, well, what does this mean then? What sort of values do you get out of a formula like this? Let's have a look back at the calculator. And we ended up with this window, which was a scatter graph. But notice down here, look at calc. Oh, if you want to choose calc, you have to hit F1 in there. And then you get this window. Okay, and we want to do some calculations. Now, this is on the Casio 9860 Plus, and what we're going to do is we're looking at the linear association, linear correlation or correlation. So we're going to try and fit a straight line through this data. In other modelling uses with this calculator, you might use other of these options. And there's more on the next page. So what we're going to focus on now is the meaning of that x there. It means we're going to try and fit a straight line through it. Y equals mx plus c or ax plus b, something like that. So that's the one we want, because we can see our form here is basically linear. So we're going to try and fit a straight line and look at the how well that line fits. So what do you want to do? If you want that, you've got to choose F2. If you hit F2, we get this window, and then you have your choice of which of these straight line forms you want the calculator to state its line of best fit in. And that, by the way, is the subject of the next presentation. how does the calculator get a line of best fit? I'm just popping in here because you have to do this on the Casio to give you an R value. Okay, so let's just choose this one. Doesn't matter which one you choose. So choose that one. You'll hit F1 in there, and up you come with this window. Now, the only thing we want at this stage, the next presentation, is about linear regression, fitting a line, and there you are, you can see it there, linear regression, producing a line of best fit, the best line we can draw through the data points to describe what's going on, and there are the coefficients in the formula. But this is what we want here at the moment, R and R squared. Okay, so there's the R value. 0.980967. What does it all mean? Is that good? Is that a high and strong correlation? I think it was, because that data was pretty tightly around a line. Let's have a look more closely at what sort of values now the product moment coefficient can take. Okay, so let's do a summary here, again from Pearson's. So here are some values, which go to there. Properties of the correlation coefficient. It measures the strength of the linear association, how close those points are to forming a straight line. And it's got to be two quantitative variables. You can't do this with non-quantitative data. We're working with numbers and means, standard deviations, as we've seen before. The coefficient makes sense only if there's a linear relationship. Okay, but it doesn't prove it. It does not prove it's linear. It's a measure of how tightly associated the two variables are in a linear pattern. Okay, if we see a linear association, the coefficient describes its strength. Outliers can distort it, so we pay special attention, as we did before. We talk about the hybrid car as giving you a different reading. It's well apart from the main body of data, and we would probably exclude it and look at the pattern of the others. Now, this is what we're after. The correlation is always a number between -1 and 1. Values of R near naught indicate a weak relationship. No significant correlation or association. Values close to 1 or -1 indicate strong association. So let's look at this. I've put the numbers in underneath now. This one we said was perfect. It's a perfect straight line. Perfect is 1 out of 1, if you like. So R is +1. It's plus because, as you can see, as the independent variable increases, so does the dependent variable. This is less tight. Try to put a line through there, and we'll be doing that later on. You can see it doesn't fit a straight line perfectly. It's got a correlation coefficient of 0.8. And so as it becomes more dispersed away from that linear model, we are getting a lower R value. So down here, would we fit a line? Would it be meaningful? No, we'll talk about that in the next presentation. But it's getting a bit ridiculous in these last two here to suggest there is much of a linear relationship or correlation between these two. The points are a long way from the line. What about down here now? It's perfect again, a perfect straight line. A linear model describes each of the data points perfectly. So there is a R value of 1 out of 1, if you like. -1, because as the independent variable increases, the dependent variable is decreasing, opposite direction, so it's a negative correlation. This is pretty tight still, but it's negative, so R is -0.8, and then it's drifting away from a straight line, weaker correlation, and here very weak, -0.2. Okay, so closest to 1 or -1 is the strongest association between them. They form more tightly a straight line. Okay, now R does not change as we change units of measurement. Okay, because if you looked at it, x minus x bar on sigma and on standard deviation and so on, it will not produce any final units. It has no units, but it's also not a percentage. It's a number out of 1, if you like. It's 0.85. You do not call it 85% as such. All right, got the idea. So now I've given you a tool for working out how closely these quantities are associated by giving you a correlation coefficient which measures, come up the top here, correlation coefficient measures the strength of the relationship in a linear pattern. All right, let's go down and just do a little bit more and see if we can see where we can analyse this further. Okay, correlation between two variables, here we are, means a relationship, I like. Pearson's are saying here it's an association. Now this is very, very important. It doesn't mean that one of them causes the other. Okay, correlation does not mean causation. Correlation does not mean causation. Two variables can have a strong correlation without one of them being the cause of the changes in the other. There may be a strong correlation between the amount of crude oil imported by a country and the rate of birth in that country, by country X, and the rate of birth in country Y. That does not necessarily mean that the increase of oil imports causes an increase in birth rate. There might be another factor. Economic growth is good. Though they import oil, they also think about having more children in the family. So there's an outside factor influencing changes in both of them. In some cases, and I've got a good one for you in a minute, there may be a causal relationship. For example, increase in level of income in a certain country and the decrease of unemployment can have a strong negative correlation. Decrease of unemployment. So unemployment goes down as the level of income goes up. This association is also causal. There's more money around and therefore it's causing a decrease in unemployment because people can get jobs. And what about the one back in the 20th century, which was finally resolved, where as the level of smoking cigarettes went up, so did the incidence of lung cancer. Okay. Or cancers. So, smoking and lung cancer. And people said for a long time, that does not prove that smoking causes lung cancer. And that argument is, unfortunately in this case, true. It's not true that smoking doesn't cause lung cancer, but we, as statisticians, we saw the figures. Stats implies figures and associations. What happened then, we had to go away and for the biochemists and biologists to show that causal. And they did. They went to cigarettes and found a chemical and then used that on mice to show that it actually produces cancer. So you have to go through this. Mathematicians, statisticians can't say it causes. We can say, all right, if you increase smoking, the incidence of lung cancer increases. But they might also, the smokers might also be doing something else. They smoke a lot, but they also do something else, and that is associated or causing lung cancer. So you have to go away and do the chemistry. You have to say, well, in smoking, is there a chemical? And yes, that chemical produces lung cancer. Up here, Pearson's saying the task of proving the causal relationship comes with economics. You have to actually show that if you increase the level of income, why would that cause a decrease in unemployment? Okay, so that's an economic argument there. All right, so we can't, as statisticians, use the word causes. If it is suspected from statistical work, it goes on to other people to prove that causal relationship. Okay, let's keep going. It's interesting stuff. Very important. Okay. Now, I want to do something here from Pearson's, because I really do agree with including this in the course, but the IB will not be examining this. Okay, this measure of r squared is not required for your exam. But did you notice it down here? Come down to the calculator. There's r, and the calculator has also provided r squared. Why is that? R squared is known as the coefficient of determination. It reports the portion of variation in one variable that can be explained by the variation in the other. Well, in other words, it's a percentage variation in one which is attributable to the variation in the other. I like the word attributable. Okay, so if we do this car data that they did before, I didn't use it all, I used some of it, r squared is 0.879. If there aren't any other changes, that means 88% of the variation in city consumption can be attributable or can be explained by the variation in the highway consumption. There is that this particular car has a highway consumption of 10 kilometres per litre, and we can associate 88% of the variation of the city consumption to that. Okay, so they're following each other with that percentage, if you like. Okay, what about example 5 here? Metabolic rate, R was 0.84. When you square it, goes right down to 0.7. We would say about 70.6% of the changes in metabolic rate can be explained by changes in the lean mass. Okay, so there's another significant factor in there apart from just the lean mass change. Okay, and in an example down below here in a minute, R squared is that, which means approximately 90% of the variation in weight could be explained by variation in the height of the teenagers down below. Well, let's have a look at that in a minute. Before we go though, some people like to talk about the strength based on the R squared value, not the R value. So here's some idea of what words you might use. This one, this screen clipping here comes from Hayes and Harris. So if R squared is, if R is naught, R squared is naught. No correlation. If R squared is between 0 and 0.25, very weak. Between 0.25 and 0.5, weak. So it all goes up in 0.25. It's easy to remember. 0.5, 0.75, moderate. This is where it gets interesting, because what we can say here with a stronger correlation like this, it's worth trying to fit a line and using it maybe to predict what's going on. But if it's only down in this region, the line doesn't describe the data set very well, does it? That's a subject of linear regression coming up in the next presentation. So these numbers are useful in deciding whether you have got a situation between these two variables, the association between them, which is close enough for you to bother trying to model it with a actual linear formula or linear model, and we'll get the calculator to do that. Let's have a look at this data down here. And this had, oh yes, it's fairly tightly associated here, height in inches and weight in pounds of these people, and you can see, yeah, they're pretty close to a linear model there. And the Pearson said R squared is approximately 90 point something, I think it was. R squared is approximately 90.7, I think, which implies 90.7% of the variation in weight is due to the variation in height. So this is the dependent variable. So we say 90.7% of the variation in weight is attributable to the variation in height. So that's a pretty dominant factor. And obviously it's not the only factor, because this is not a perfect straight line here. There is some deviation away from it, suggesting that other factors are involved. Interesting, isn't it? Because we can take data and get some real meaning out of this by trying to associate pairs of variables and their relationship to each other. All right, let's have a look at some examples. Again from Pearson's. The table below gives you the data for a lab experiment involving the length of a metal alloy bar using electronic equipment when it's exposed to heat. So yeah, we'd say heating it was independent, and in response, or what's dependent, it's going to expand and get longer. Okay, draw a scatter plot. So I've given you an idea of how that should look. So here, yep, heat on the bottom, that's the independent variable, and length is going to expand, is going to get longer, so that's dependent. Oh, yeah, there's the scatter plot. The line doesn't fit very well, does it? Relatively strong relationship, they've said here. Okay, moderate to strong, I would have said. I don't know. Does that agree? Oh, no, the R squared comes up as 91.2. And so that you would say that was strong. Okay, the R is 0.95521. So we take that from the calculator, and so we can say, and this is not in the course, you don't have to be able to make this comment here about R squared at all. But I like together with Pearson's, think it's a worthwhile aspect because of this idea that you can say a lot of the change in the dependent variable can be attributed to the other one. It gives you an idea of how much that's a factor in what's happening to the dependent variable. Okay, all right, so let's keep going, and this is your turn now. Okay, so I'll put up question 1 and 2. The fully worked solutions are coming on below, all of them. So question 1 and 2, if you could pause the presentation and have a go. Come down now to question 3. Just come right there. Let's see if we can get all the... no, we can't get the data on. So we'll just drag this up a bit. So read the question, and then I'll scroll it down so you can get the whole set of data, because you're going to need that for a scatter plot. So we come down, I'll just go back a little. Okay, so there are the questions, make a scatter plot, etc. So you need to put all of that data in list 1, list 2, whatever way around you're going to do it. Describe the relationship, etc. So there's the question. Okay, have a go at that one. And then question 4. Okay. All right. I'll take you down to the answers now, one by one. Okay, there's question 1. Question 2. We'll just go down a little bit here for question 3. And finally, question 4. All right, so I hope you're getting a bit excited about this, because this has got implications, hasn't it, in the real world. All right, well, that's it for this presentation. You can see where we're going to finish this part of the statistics course off. We want to actually try to fit an actual line through there and talk about, can we use that to predict inside the data set and outside the data set and define those things. So that's going to be a bit of excitement for later on. But for now, it's cheers from me. Catch you in that